I'd like to show just a small part of a work of a former master student of me, Danilo. He developed some studies on the use of Bayesian Inference on quite general class of inflated beta regression models. Also developed some studies on residual analysis. And what I'm gonna show here is just a small part, as I said, and this part corresponds to a part of a wide simulation study that he developed in his master thesis. Okay, just a brief review about regression models for limited response variables. I think that everybody here is familiar with that. So you have a response variable that is limited somehow on an A-B interval, and particularly when this interval is naturally A equals to 0 and B equals to 1, or if you want to transform this A-B interval and in a 0-1 interval, it's possible to do that. You have what we call as a proportional data. And this proportional data can arise when you have, for example, a proportion of let's say, of trees in a region that presents some kind of disease, for example, or a proportion of persons that did not pay some kind of expense, for example, credit card, and so on. And in this case, we have, and sometimes we have, besides a 0-1 interval, this response variable can present 0 and 1 values. So we have the so-called inflated data sets, and the regression models that are generally used to model this kind of data are called inflated regression models. And one of the, perhaps the most used kind of inflated regression models is the so-called beta inflated regression models. Well, one of the first works, it was not the first one, is that one developed by Ferrari and Privari, sorry, by that mistake, in 2004, and they somehow developed a beta regression model proposing a reparametrization of the usual beta distribution, and in this work they modeled it by a regression structure using a logit link function, the mean of beta distribution. The precision parameter in that work was not modeled. In this work, for example, Ospina and Ferrari proposed a 0-1 inflated beta regression model. Different from that, where only values in the interval 0-1, not including 0 and not including 1, were possible. Here, it's possible to have in the data 0 and 1. Well, these works basically focus on the using of frequentist inference for parameter estimation and model diagnostics. Well, this work of this dissertation was finished last year, and that time I did not know, and neither Danilo, some work using Bayesian inference to estimate parameters of beta regression model. Nowadays I know that there are some works, for example, I know at least one from Diana, that use Bayesian inference to estimate the parameters of inflated, some kind of inflated beta regression models. Okay, let me show you just a little bit of a review and go over this work. Just let me show you the model. This model, this distribution, was first proposed by Ospina and Ferrari in 2010. This only probability distribution, and we can recognize that as a finite mixture between a Bernoulli distribution and a beta distribution. So this probability distribution consists on to give a probability mass to 0 and 1 values, and another probability mass for values within this 0-1 interval not considering the extremes of this interval. So we have basically a finite mixture of two distributions, a Bernoulli distributions and a beta distribution. These authors propose this probability distributions. And here we have the beta distribution parameterized in terms of the expected value mu and the precision parameter phi. The precision parameter has the inverse mean of the value of the scale parameter. That is, higher is the value of the precision parameter, smaller is the variance of the data. So the 0,1 inflated beta, 0,1 beta inflated regression model was proposed by Ospina and Ferrari in 2012, and it consists on modeling not only the expected value of the beta distribution, but also the modeling the precision parameter, the delta parameter that represents the probability of observation to be inflated, and also the modeling by a regression structure, the delta parameter, that is the probability of observation be equals to 1, given that it is inflated. Okay? So they model by a regression structure these 4 parameters. They use a logistic linking function to expected value. They use also a logistic linking function to model the delta and the gamma parameters, and they use a log link function to model the phi parameter. In this work, Danilo only used only modeling the mean parameter by a regression structure. The other parameters were estimated without any regression structure. So therefore we have these 4 kinds of parameters to be estimated, and basically what I'm going to show to you is how it's possible to do Bayesian inference for this 4 set of parameters, and also to compare our results from Bayesian inference to that ones developed by Ospina and Ferrari in terms of frequentist inference by using maximum likelihood estimators. But it's possible, one thing interesting here that's very related to any kind of mixture distribution is that it's possible to rewrite the likelihood in terms of some kind of augmented data. This augmented data can be observable and can be unobservable. In this case, it's possible, we know if observation is inflated or not. In this kind of setup, we are 100% sure that if we have observation comes from a beta distribution, or if this observation comes from a Bernoulli distribution. So we observe this kind of indicator variable. And in this work we denote hereby a ZT variable, assuming 0 if the observation comes from the beta distribution, and assuming 1 if the observation comes from the Bernoulli distribution. So it's very easy to show that, it's not so hard to show, that the likelihood for one observation can be written like that. And it's very useful to written like that because, for example, we can implement an MCMC algorithm, for example, by using ISBrA in a more straightforward way. And also for these two parameters, gamma and delta, I'm going to show you that we have closed form for the posterior distributions. So it's not necessary to use any kind of numerical algorithm to sample from these distributions. So it's not easy, it's not so hard to show that. So you have that the entire likelihood can be written like that. And one thing that is very interesting that is the fact that the likelihood is, let's say, partially separable, because we have one part related to beta and phi, another part related to gamma, and another part related to delta parameter. So we have something like that in the likelihood. And in this work we considering 4 sets of prior distributions for beta and phi. One of them we call usual one, assuming independent normal distribution for beta and a gamma distribution for phi. We also consider the independence Jeffreys prior for the two parameters that are not so hard to calculate because we have in the literature the information feature matrix are available. We also used the Jeffreys prior distribution that is not an independent prior. And finally we have what we call an improper prior distribution, since we are assuming prior distribution for phi proportional to a constant. And also, for conjugate reasons, we are assuming a beta distribution for delta and gamma parameters. So under the setup, we have that the full posterior distribution is like that if you are using the prior distributions 1, 2, and 4. And if you assume a Jeffreys prior distribution for beta and phi, we have this posterior distribution. So only for delta and gamma is possible to obtain the exactly posterior distributions. And they are beta distribution as well, the prior distributions with these hyperparameters. But to beta and phi is not possible to obtain their marginal posterior distributions. So in this work we use the MCMC algorithms, and unfortunately it's not possible even to obtain a closed form for the so-called full conditional distributions for beta and phi. And what Danilo did is to implement in R. We did not use WinBus. The Metropolis has an algorithm within Gibbs algorithm to simulate von beta and phi. So the full MCMC algorithm can be summarized as follows. You just start with suitable starting values, initial values. So we simulate beta from their conditional distribution. Then we simulate phi from their conditional distribution. We repeat this process until to reach some convergence. And after that, we can estimate delta and gamma by using their posterior distributions. And it's very interesting to note that this posterior distribution do not depend on beta and phi, since the likelihood is separable. Well, I'm going to show you just a small part of the simulation study that Danilo developed. That it consists on to replicate 100 times, that is, to generate 100 sets of values response, considering a 0 and 1 inflated beta regression model with this parameter equals to 0.5, that it corresponds to, again, the probability to have observation equals to 1, given that it is inflated. Also, we assume some usual and reasonable values for beta and phi. I'm not going to through that with details, but we consider different situations, varying the number of subjects, varying the number of covariables, also the value of the phi parameter. Remember that higher is the value of the phi, smaller is the variance of the data set. We also consider different values of observation to be inflated. And I'm going to show you just a few parts of these results. Also, in terms of prior distributions, we consider, instead of 4, 5 sets of prior distributions for beta and phi. The first one is the usual one that I showed you a few minutes ago, a few minutes before. It consists on bivariate, a multivariate normal distribution, with zero mean, and a diagonal matrix of covariance. For phi, a gamma distribution that has a higher value of the mean, 500, and an even higher variance. The second set is the same thing for beta, but gamma prior distribution with even a higher variance than the first one. The third one is independence Jeffreys prior. The fourth one is the Jeffreys prior, and the final one is the improper prior with the same structure for these two prior distributions. For gamma and delta, we are considering the uniform prior distributions, that it corresponds to a beta distributions with the hyperparameters both equals to 1. Okay, and for example, notice that we consider this prior structure for gamma and delta. For example, the maximum a posterior estimator is numerically equals to maximum likelihood estimator. So what I'm going to show to you is the results from expectation a posterior estimator. So we consider the usual statistics to compare the accuracy of estimators, the square root of mean square error, and the average value of the relative bias. Okay. So in red you can notice for each situation the set of estimated that presented the most accurate results. For example, by considering a real value for phi equals to 50 and the sample size equals to 20 with 5 covariables and the value of delta equals to 0.3, remember that we are in the setup of 0 and 1 inflated beta regression model. We can notice that the independence Jeffreys prior showed or presented the most accurate values for the regression parameters, betas. Okay? Here is just a summary of the statistics, average value for relative bias for all betas parameters. So I have 5 regression parameters, and here is just a mean of this statistics for each one of these parameters. Okay? So here we have that independence Jeffreys prior, for example, presented the most accurate values or estimated. Here the usual one set of priors present the best ones. Again the Jeffreys prior here, the independence Jeffreys prior, the Jeffreys, and the usual one. In no one of these setups, the maximum likelihood estimators presented the most accurate results. Again, for phi parameter, only the Jeffreys priors and the independence Jeffreys priors presented the most accurate results. Okay, and we noticed that especially for phi parameter, the Jeffreys and the independence Jeffreys priors produced the most accurate estimators, considering the whole set of estimators. For delta and for delta parameter, we have that the maximum likelihood estimates compared to the expectation a posterior estimators presented better results. But we need to keep in mind that, as I said before, that in this case maximum likelihood estimates corresponds to the maximum a posterior estimated under this prior distribution. So in some sense we are saying that the maximum a posterior estimates are better than the expectation a posterior estimates. So again we have that the Bayesian estimates conclusion presented the most accurate results. But in this case we need it's better to use the maximum a posterior instead of the expectation a posterior. That's the conclusion. Okay. And for delta parameter, again we have that the Bayesian estimates that in this case corresponds to the expectation a posterior estimates presented the most accurate results. And again, the maximum likelihood estimates in some sense are not the best option to estimate the parameters.
What is EBEB?
It's the average value for the relative bias. I calculate the bias, take the value without the signal, and divide it by the true value of the parameter without the signal. And finally here, we can notice that, or we cannot not notice that for beta and phi parameters, in terms of the square root of mean square error, that especially for small sample size, we have the most accurate results. Here is not so easy to see, but look at here. We have the Jeffreys prior distribution here. Here we have the independence Jeffrey prior distribution here. Look at the triangle. Here we have the usual prior number 2. Here we have the proportional prior distribution. Here we have the usual prior, and here we have the maximum likelihood estimates. So in conclusion, we can see that especially for phi parameter, the precision parameter, the Bayesian estimates produce the most accurate results. Of course, it takes much more time to have results from an MCMC algorithm than if you want to decide to use the maximum likelihood estimates by using some kind of optimization algorithm, just like Newton-Raphson, Fisher scoring, something like that. But we are saying that here, that if you want to obtain most accurate results, and I think that is very important, it's better to use the Bayesian estimates. Well, here there are some conclusions. As I said, it's just a part of work of Danilo. Danilo also developed some Bayesian tools for model diagnostics. Here I just present some part of the simulation results, but in my opinion, the best, the most important result concerning this part is that and of course I like so much to use Jeffreys price distributions, is that the Jeffreys price distributions and the independence Jeffreys price distributions produce the best or the most accurate results. For me, this is the most important result from this work. So some reference here, and sorry by my poor English. Thank you.